And I'm Henry.
And we're going to be presenting on NMR, nuclear magnetic resonance.
Apologies for our camera blocking out some of the details of the slides.
Yeah. All right. So brief history of NMR and quantum mechanics. NMR were discovered in 1938. It's, as of that, it's a pretty recent physical discovery, pretty much following directly after spin in 1933. MRIs were discovered even more recently in the 70s, making them a very modern field. That being said, they both build off of a lot of quantum mechanical discoveries and even classical discoveries from much earlier in the 1900s and even 1800s that we have kind of talked about in this and other physics classes.
All right. Since its discovery, NMR has been a very big deal, at least in terms of recognition across scientific disciplines. Specifically, the most notable examples being the 6 Nobel Prizes across physics, chemistry, and medicine, which have all been given to researchers in the field of NMR or MRI. Starting in 1943 with the nuclear magnetic moment, and then in 1944, the discovery of NMR was honored. And then all the way in 2003, 50 plus years later, MRI and major improvements in MRI was honored. And this makes it, I would think, one of the most awarded physical phenomena in science, and which is pretty cool and pretty unique, especially since it has so many different disciplines.
Yeah. So before we kind of get into the nitty-gritty details of NMR, we're going to start with a brief overview of spin, which is an intrinsic property of all particles. I'm sure everyone's heard about spin to at least a little bit of an extent. Like other quantum measurables, spin has an operator or operators. It uses both S and I. You'll see both in our presentation. And it obeys all rules for quantum measurables that we've discovered in our class so far. Interestingly, the spin operator in one direction does not commute with the spin operator in another direction, for example, like X spin and Y spin. And because spin obviously obeys the generalized uncertainty principle, therefore you cannot know both the X and the Y spin at the same time. Unlike some measurables that we've also discussed in class, spin comes in packets. It comes in, depending on the particle, the original particle, it can come in packets of multiples of 1/2 or 1. And these are invariant in the particle. However, they can change or flip somewhat freely between positive and negative. This is, like other quantum measurables, defined by a wave function and therefore inherently probabilistic and unknown until it is directly measured. Kind of having said that, spin is a really complicated topic that you could do a whole presentation on or more. So for the sake of this presentation, that is all we'll need to know. I'd also like to just add that we will only be thinking of spin in the z direction for the rest of this presentation. That's all we'll need. And we're going to treat spin as intrinsic angular momentum, which means that all particles have, what they would have given an angular momentum. So because they're charged in our case, a magnetic dipole moment, we can define that as mu equals gamma s, where again S is the spin operator, and mu is another intrinsic property called the gyromagnetic ratio. And we will use that very soon.
So, building upon the concept of spin, a couple different physics, quantum mechanical experiments and discoveries that are helpful in understanding NMR are the Stern-Gerlach experiment and the Zeeman effect. The Stern-Gerlach experiment, which we've discussed in class a little bit, takes an inhomogeneous magnetic field, which is different than NMR, where we have a homogeneous magnetic field. But it shows that when you have this beam of particles, as seen on the left, you can just in a magnetic field split them into 2 different beams, one for spin up and one for spin down, which is a very clear way of demonstrating the quantization of spin. And then the Zeeman effect, which is more directly applicable to NMR, but was originally observed as the splitting of the emission spectral lines of hydrogen in a magnetic field. Really complicated, but we essentially in NMR exploit this by noting that when you're splitting the spin states, because the spin states are discrete, when you put them in a homogeneous magnetic field, you can notice that there's an energy difference between the two spin states, which originally, and in the Stern-Gerlach experiment, might have the same energy or might not. But when you split them into two different energy states, one associated with each spin state, you can then exploit that to make some NMR measurements, which we will soon explain. And this energy difference is given by, again, the gamma times B, essentially, which is the magnetic field that it's exposed to, and the gyromagnetic ratio, which is determined by the magnetic dipole moment, and thus the spin.
All right, so how can we use this to our advantage? Since particles have this intrinsic magnetic dipole moment, they are acted upon by the external magnetic field. This field, like Henry explained, splits the spin states into two different energy states that are being aligned and where the magnetic dipole moment is aligned and anti-aligned with the magnetic field. And these states precess around the B field. They just kind of wobble around in time. This precession occurs at the particle's Larmor frequency, which is a very important frequency, defined as the, once again, the gyromagnetic ratio times the B field.
I'm so sorry, but I did.
Sorry about that.
We're back.
Let's see. So this Larmor frequency is defined as, once again, the gyromagnetic ratio times the strength of the magnetic field. Now, these states have different energies, as you can kind of see, hopefully not too covered by our camera, separated by delta E, which depends on a multitude of factors, but it's mainly due to this potential, once again, acting on the magnetic dipole moments of the particles. Inputting energy to these aligned particles, usually via an RF pulse, can knock them into higher energy states where the magnetic dipole moment is misaligned with the magnetic field. This kind of causes all the particles to jostle a little bit and transition into these higher energy states, which then can decay back to the lower energy states, releasing a photon to cover up for the kind of missing energy. And this decay occurs also at the Larmor frequency, so it is super important. And later you'll see how this comes into play on how we measure things.
So connecting this idea of using spin to our advantage to the Hamiltonian and to measuring the energy and the eigenstates of a system, we can kind of connect back to the Zeeman effect and consider that because the discretized spin states, spin up and spin down, have associated energy, by measuring the spin of the state mathematically, we can form a Hamiltonian where we take the homogeneous main magnetic field B0 in the z direction and dot it with the spin operator, giving us just the z component. And so using our time-independent Schrodinger equation and applying this spin/energy operator, since it essentially is the spin operator, but the spin operator is functionally the Hamiltonian with some extra factors dependent on the spin, we can get out the spin eigenstates, 1/2 h bar or -1/2 h bar. But because these have energy levels associated with them, we are also computing the energy with a factor of gamma, b, and then our wave function psi. It's obviously in reality a little more complicated than this, and then once we add in the RF pulse it becomes much more complicated. But to do calculations with the RF pulse, you would generally use change of coordinates to transform into the rotating frame that is oscillating at the same frequency as the time-varying B1 field, which is the RF field that we use to perturb the particles. And in this way, you can make predictions, much more detailed predictions about the state of the system. But for our case, this is just a simple explanation of that we think connects well to this class.
All right, so now that we've kind of gone through all the parts, I'll just take you through a quick timeline of how we actually use NMR to measure a sample. So as kind of we've already covered, the particles in a lower energy state absorb an RF pulse and transition into a higher energy eigenstate. This state, however, is unstable, so the particle then decays back to its original lower energy state and releases a photon. This photon can be detected, picked up using an RF coil, and then that can be transferred into a current, which we can amplify and measure. In the singular particle case, we can measure the time that this decay takes, which is equal to the Larmor frequency, which is unique to each particle or each atom. And we can also separately scan through different RF frequencies and see which frequency the particle reacts best to, which would also be the Larmor frequency, or at least related to the Larmor frequency. And therefore, we can kind of pick out the type of material or element that it is. How does this change for bulk materials? In a single particle example, the magnetic dipole moment becomes fully aligned with the magnetic field, and then when hit with the RF pulse, fully aligned in the XY plane with the RF pulse. In a bulk material, due to intraparticular forces and just other electrical forces kind of coming and going due to other atoms, you don't get a full snap to the Z or B field plane and then the RF plane. You just get a slight shift. We can still use this as the bulk magnetization still kind of follows with the B field and the RF field, or RF pulse. And we can still kind of detect how the particles decay back into their original states. However, a lot more detailed data analysis is required to extract that information and separate these kind of smaller changes from other smaller changes. Kind of similarly to measuring a single particle, we scan through RF pulses at different frequencies and detect how different parts of the sample reacts and how much of the sample reacts to each frequency, which can tell us the chemical composition of a sample, which is super cool.
So finally, now that we have an idea for how this works in the case of a bulk sample, there's really only one final addition to our NMR system that we need to get MRI, and this important piece is the gradient coils. The gradient coils add in the spatial dependence that is needed to construct a 3D image. Basically, they create a magnetic field themselves that opposes or aligns with the main magnetic field in such a way as to create a gradient of the magnetic field spatially, which allows us to encode position information about where we're getting different data from. And using this, we can put together these beautiful images of, inside of the human body, which can be used for diagnostics, research, lots of really cool things. And it's really one of the most amazing applications of NMR and one of the coolest tools in medicine. It's a super important one for sports injuries, concussions, cancer diagnostics, and things like that. And it's safer than a lot of other imaging techniques such as PET, X-ray, and CAT scans because it doesn't really involve harmful radiation like a lot of other tools. And it's continuing to be improved all the time. There's a research group at NIST doing research on this, as well as at other universities and research institutes around the world. And so NMR is a very active field of research in chemistry and medicine and physics, and we just think it's really cool. And MRI is an especially cool application to round out this presentation.
Thank you.
Thank you. Here's some things if you want to look at them real quick, but we'll send you the slides. Thank you.
Thank you.